By the close of the 19th century, Melbourne had outgrown its original man-made water supply, the Yan Yan system. Pioneering in its time, was now straining under the pressure of a booming population and an increasingly thirsty city. The need for more reliable and higher quality water was undeniable. City planners and engineers looked east to the forested mountains of the Yarra Ranges, where steep terrain, dense vegetation, and high annual rainfall presented an ideal solution: the Watts River catchment. This region would become the backbone of the Watts River scheme, Melbourne's next great leap in water supply planning, and it all began at Fernshaw. In 1891, engineers completed construction of a diversion weir on the Watts River at Fernshaw. This simple but effective structure allowed water to be diverted into the newly built Maroondah Aqueduct, transporting it more than 60 kilometres by gravity alone into Melbourne's growing network. The aqueduct included open channels, siphons, and tunnels designed to follow the terrain with minimal mechanical input. It was a smart, low-energy solution and had a significant improvement on what had come before. Fernshaw was a deliberate choice. Remote, wet, and sparsely inhabited, the catchment surrounding the weir was quickly designated a protected zone, with no settlement or agriculture permitted. This introduced the concept of closed catchment to Victoria's water management practices, preserving water quality at its source. The Watts River scheme provided a short-term boost, but engineers knew a diversion system alone would not be enough. Seasonal variability and limited holding capacity meant the system lacked the resilience needed to support long-term growth. In the 1920s, the next step in the plan was realised. Construction began on the Maroondah Dam, located downstream of the original weir, which would later be inundated by the impounded waters. Completed in 1927, the dam created a reservoir capable of holding back more than 22 gigalitres of water, massively increasing storage capacity and improving flow regulation into the downstream aqueduct, still heading towards Melbourne. The dam wall was constructed as a concrete gravity dam, a well-established dam design at the time. Combined with the existing aqueduct, the completed Maroondah system offered a reliable, high-quality supply for a growing Melbourne. But as demand continued on a never-ending rise, attention shifted further east to another pristine catchment, the O'Shanassy River. Here in 1914, engineers had already completed an aqueduct to capture and deliver water directly from O'Shanassy River to Melbourne, supplementing supply even before a dam was built. This aqueduct was part of a long-term plan. It was built in anticipation of a major storage project, one that would eventually take place further upstream. That project became the O'Shanassy Reservoir. Completed in 1928, the dam added itself only 3 gigalitres of storage to the system, but like Maroondah, the area benefited from a high rainfall, densely forested catchment, protected under closed catchment rules. The high yield of this catchment and small storage would mean that this asset would become a major workhorse within the growing water network. One particularly novel feature of the original dam design at O'Shanassy was the original siphon overflow mechanism. Once the reservoir reached a certain level, the siphon would activate and continue draining water until the level dropped to a safe threshold. While effective, it was apparently loud and imprecise, and somewhat intimidating, eventually replaced with more modern systems for improved flood and flow control. Together, Maroondah and O'Shanassy represented a turning point in Melbourne's water story. These weren't just isolated projects, they were part of a coordinated effort to build a resilient, regionally integrated network. They also introduced 3 core principles that would guide Melbourne's water strategy for the next century: closed catchments to protect water quality, gravity-fed infrastructure to minimise energy use, and redundancy, multiple supply sources to safeguard against failure or drought. Not every proposal of the time made it into the network, however. In 1900, the board proposed diverting water from the Acheron River across the Great Dividing Range, similar to Yan Yan, but that plan was met with heavy opposition from inland irrigators. Although approval was briefly granted during the 1907-1908 drought, the requirement to compensate those affected throughout inland Victoria ultimately rendered the project too costly. The Acheron scheme was shelved, never to be revisited. But another idea quietly advanced. Even before the O'Shanassy Dam was completed, engineers had turned their attention to the Upper Birrarung. In 1929, the board began construction of a new aqueduct, one that would transfer water from the Upper Birrarung and feed it directly into the O'Shanassy system. This 24-kilometre aqueduct and conduit brought in high-quality water from yet another catchment, increasing the overall capacity and reach of the water network. While the Upper Yarra Dam itself wouldn't be completed until the 1950s, owing to World War II, this early aqueduct laid the groundwork and gave access to the water itself. It was a calculated move, designed to expand the system's capacity ahead of future need and position the Upper Birrarung as a future source of a reliable supply. By the end of the 1930s, Melbourne's engineers had successfully transformed the city's water system. From a single source at Yan Yean, the network had grown into a multi-reservoir, gravity-driven system, supported by protected catchments and forward-thinking planning. But as the water flowed into the city from the mountains, a new question was emerging. How would it all be stored, balanced, and distributed within a rapidly urbanising Melbourne? In our next episode, we'll explore how engineers answered that challenge with the construction of Sylvan, Upper Yarra, Greenvale, and Cardinia reservoirs, designed not just for supply, but for regulation, storage, and metropolitan distribution. I'm Paul Michael Angus. Thanks again for joining me.